Hi there! Did you know that just by analyzing the light from a star, we can uncover its secrets, like what elements it's made of and how hot it is? It's like reading the star's diary just by looking at its spectrum. In this video, we'll learn how astronomers unravel the mysteries hidden in the spectrum of a star. Let's begin. Even before we begin talking about the spectra, we have to mention Annie Jump Cannon. Annie Cannon was one of several women hired by the then director of the Harvard Observatory, Edward Pickering. At the turn of the 19th century, astronomers were engaged in finding the best possible classification scheme to understand the wide variety in spectra of the observed stars. In the year 1901, based on the prior suggestions of her mentor and colleagues, Cannon rearranged the spectra such that the scheme turned into a temperature sequence going from the hottest O-type stars to the coolest M-types. Between 1911 and 1914, Cannon classified 200,000 spectra of stars. Her results are recorded in the Henry Draper Catalogue. Even today, many stars are referred to by their HD number. Cannon's classification came to be known as the Harvard classification scheme and is used by astronomers to date. Today, there is the Annie Cannon Prize, which is awarded to women astronomers who have made outstanding contributions in this field. So what's this whole stellar spectra thing about? Well, stellar spectra are basically the fingerprints of stars. By studying the light they emit, we can learn a ton about their composition, distance, surface temperature, luminosity, and many other properties. Stellar spectra, such as those shown here, are essentially black-body spectrum superimposed with dark absorption lines. These lines are formed in accordance with the Kirchhoff's laws as discussed in the previous video, a link to which is provided in the description below. The Harvard classification scheme is a temperature sequence of the stellar surface. Generations of astronomers have remembered the sequence using this mnemonic. The fact that Pickering and Fleming's original classification from A to Q was based on the strength of hydrogen lines implies that despite being third in line in terms of effective temperature, the A-type stars have the strongest hydrogen lines, while the O-type stars are the hottest, yet have the weakest hydrogen lines. Cannon further added subdivisions represented by numbers 0 to 9 within each class, with 0 being the hottest and 9 being the coolest in each spectral class. The Sun, for instance, is a G2 star with an average surface temperature around 5700 Kelvin. The subdivision in Cannon's spectral classes were based on the ratios of certain absorption lines as shown in this example. We'll get to that towards the end of this video. It is interesting to note that at the time of publication, the physical basis of the Harvard classification was unknown. Astronomers figured that the Balmer lines in Vega, which is an A0 star, are much fainter than seen in the Sun, while the calcium lines are much stronger in the spectra of the Sun than in Vega. But they were not sure if the difference in surface temperature alone explained this variation in stellar spectra. The key to the mysteries of the stellar spectra came about with the theoretical understanding of the quantum nature of atoms. But first, let's learn about the strength of spectral lines. Astronomers have devised the concept of equivalent width to measure the strength of a spectral line. Simply speaking, the equivalent width of a line is the width of a perfect rectangle having the same area as the spectral line, which would run from the continuum all the way down to 0. That is, the point of no light at all. In the shown example, for instance, the spectral line has an equivalent width of 2 angstroms. But how are absorption lines produced? Well, you know that the core is the hottest part in a star. The outer parts of the star therefore act as a gas cloud in front of a source of continuous radiation, which is the core. As a consequence, some of the radiation at particular wavelengths is absorbed by the outer layers, resulting in light missing from those wavelengths, aka the dark absorption lines. Recall the different series of spectral lines of the hydrogen atom. All lines formed when an electron jumps to the ground state are part of the Lyman series, while the lines corresponding to the first excited state, that is n is equal to 2, are called the Balmer series, and so on. The Balmer lines are very well studied because many of them fall in the optical waveband between 3000 to 8000 angstrom. In order to unravel the mystery of the physical basis of the Harvard classification scheme, astronomers needed answer to two questions. 1. Which orbitals are most likely occupied by electrons in an atom? And 2. What is the relative number of atoms in different ionization stages? As we'll see in this video, both of these are answered via statistical mechanics, which is a branch of physics dealing with the studies of statistical properties of a system with many members. For instance, a gas with many atoms. But don't you worry about it. We'll briefly introduce two concepts from statistical mechanics here to continue with our exploration of the stellar spectra. Consider the particles in a gas moving at different speeds. While we cannot find the exact speed with which a particle is moving, we can assume it is moving in a very small range of velocity between v and v plus dv. The Maxwell-Boltzmann distribution, as shown here, graphically illustrates the fraction of particles per unit volume that will have velocity in the range of v and v plus dv. The Maxwell-Boltzmann distribution is described by this equation where n is the number of particles per unit volume, m is the mass of a particle, and T is the temperature of the system. K is the Boltzmann constant. Note that the exponent is the ratio of the kinetic energy of the particle, half mv square, and its thermal energy kT. Most particles will have energies less than the characteristic thermal energy, and the distribution peaks when the two energies are equal, corresponding to the most probable speed of particles given by root 2 kT by m. However, the distribution is skewed to higher energy particles, resulting in a somewhat higher root mean square velocity given by root 3 kT by m. The Maxwell-Boltzmann distribution is governed by a fundamental result of statistical mechanics, which is that electrons in an atom are less likely to occupy orbitals of higher energy. We know that each energy state is governed by a unique set of quantum numbers. For instance, for the ground state of hydrogen with energy of minus 13.6 electron volts, the set of quantum numbers is given as this. If SA is the set of quantum numbers governing an energy state A and SP is the same for another energy state B, then the ratio of probabilities that the system is in state SB to the probability that it is in state SA is governed by this equation. Here, T is the temperature of the system, and exponential term e to the power minus e by kT is known as the Boltzmann factor. The Boltzmann factor is critical for the study of statistical mechanics. For instance, if EB is greater than EA, that is, the energy of state SB is greater than the state SA, notice that the thermal energy kT decreases towards zero as temperature decreases. And hence the quantity minus delta E by kT tends to minus infinity, and so the ratio of probabilities tends to zero. This is expected if there is not much thermal energy present in the system to raise the electrons to higher energy orbitals. On the other hand, if there is plenty of thermal energy available, that is, T tends to infinity, then the quantity minus delta E by kT tends to zero, and the ratio of probabilities tends to 1 as expected, because if there is unlimited amount of thermal energy available, all the energy levels of the atom are accessible. But energy levels are often degenerate, that is, more than one quantum states of the atoms have the same energy. In such cases, one must account for all the energy states with same energy using statistical weights, consequently modifying the equation as shown here. Recall that the degeneracy of a state with principal quantum number n is 2n squared. This equation representing the ratio of probabilities that the system is in any of the degenerate states SB to the probability that it is in any of the degenerate states SA is governed by this equation. But since a stellar atmosphere comprises a vast number of atoms, the number of atoms is distinguishable from the number of energy states, and therefore the ratio of probabilities is the same as the ratio of number of atoms in each of the degenerate energy states as well. This is known as the Boltzmann equation. The Boltzmann equation yields that in a gas of neutral hydrogen, a temperature of 85,000 Kelvin will be required to have equal number of atoms in the ground and the first excited state. But recall that Balmer lines attain maximum strength for A-type stars having an average surface temperature of a little over 9,500 Kelvin. So how is that possible? The answer to this mystery lies in considering the relative number of atoms in different states of ionization. In astronomy, the state of ionization is represented by Roman numerals after the species. For instance, H1 implies neutral hydrogen while H2 is singly ionized hydrogen. For hydrogen, 13.6 electron volts is required to turn H1 to H2, so that is called its ionization energy. But both these atoms may not be in the ground state, so an average must be taken over all the possible orbital energies to allow for the partitioning of the atom's electrons amongst its orbitals. For this, we calculate the partition function for the initial and the final atoms. The partition function is the weighted sum of the number of ways an atom can rearrange its electrons with the same energy. As expected, the higher energy orbitals will get a lower weight. Using the partition function, the ratio of atoms in ionization states I and I plus 1 is given by this equation, known as the Saha equation after the genius Indian astrophysicist Meghnad Saha, who first derived it in the year 1920. Note that as the number density of free electrons Ne increases on the right-hand side of this equation, the number of atoms in the higher ionization state decreases, since there are more electrons with which the ion can recombine. The factor of 2 on the right-hand side represents the two possible spins of the electrons plus half and minus half respectively. Me is the mass of the electron. By combining the Boltzmann and Saha equations, it can be shown that the most intense Balmer lines will be produced for stellar temperatures around 9000 Kelvin, that is, the A-type stars. In the year 1925, soon after Saha's equation was published, in her PhD thesis, Cecilia Payne presented the variation in different spectral lines as the temperature and spectral type of stars changes. Her results suggest that there are only minor differences in the composition of stars. She was not only the first person to determine the composition of stars, but also to discover that hydrogen dominates the universe. Cecilia's results, together with the mass-luminosity relation, led astronomers to consider the theory of stellar evolution, which is actually now proven to be wrong. According to this theory, a star began its life as a hot, massive O star, and as it lost its fuel, it turned into a dim, small M-type star. In fact, the use of the term early and late spectral types from O to M find their origin in this idea of stellar evolution. If this idea of stellar cooling with age was correct, then a relation must exist between luminosity and size of stars. A Danish engineer and amateur astronomer, Hertzsprung, analyzed stars whose spectral type and magnitudes had been measured. In the year 1905, he published this expected relation between these two quantities. But he was puzzled to note that stars with spectral type G or later had a range of magnitudes despite having the same spectral class. He called the bright stars as giants in accordance with the Stefan-Boltzmann law, which shows that at a given temperature, more luminous star will be larger. While Hertzsprung presented his results in a tabular form in 1913, Henry Norris Russell of Princeton published this figure, coming to the same conclusion as Hertzsprung. He also called the more luminous stars as giants and their dimmer counterparts as dwarfs. The band containing hot O to cool M stars is the main sequence, which includes 80 to 90% of all stars. Although ignored by the creator, we now know that the lonely point in the bottom left quadrant is a white dwarf star. This plot, now known as the Hertzsprung-Russell or HR diagram, even with 200 data points, is a fair representation of its modern version. The Sun is a main sequence star. With luminosity and temperature along the two axes, this plot is also referred to as the theoretical HR diagram. Its observational version is the color magnitude diagram, which has absolute magnitude and color, two quantities measured by astronomers as the two axes. A star's radius can easily be determined by knowing its position on the HR diagram. The Stefan-Boltzmann law states that if two stars have the same surface temperature but one star is 100 times more luminous than the other, then the radius of the brighter star will be 10 times larger. On a logarithmic plot such as shown here, the stars of same radius lie along diagonal lines running roughly parallel to the main sequence. The main sequence stars vary in radius from about 0.1 to 20 times the radius of the Sun, while giant stars are 10 to 100 times larger than the Sun. The fact that most stars are arranged along a one-dimensional sequence in the luminosity temperature plane is probably one of the most important discoveries in stellar astronomy, because it implies that the properties of stars are determined by a single parameter, that is, their mass. Combining the masses and luminosity of the main sequence stars, astronomers have concluded that their density is same as water. Surprising, isn't it? On the other hand, giant stars have a lower average density. The difference in the spectra of giant and dwarf stars with similar effective temperature lies in the width of their spectral lines. This was first noticed by Antonia Mori and is shown here. Her work was carried forward by many astronomers until it culminated in the Morgan-Keenan-Kellman Atlas of Stellar Spectra in the year 1943. This scheme adds a luminosity class designated by a Roman numeral as shown here to the Harvard class of stars. In general, among the stars of same spectral type, narrower lines are produced by the brighter stars. The Sun, for instance, is a G25 star since it is on the main sequence. This result can also be understood using the concept of surface gravity defined as the gravitational acceleration on the surface of a star given by the relation G is equal to Gm by r squared. This means that the surface gravity is inversely proportional to the size of star. But from the models of stellar atmosphere, we know that lower is the surface gravity, narrower are the absorption lines produced in the spectra. Today, we know that the luminosity classes reflect the mass and evolutionary state of a star. So to wrap it all up, stellar spectra are incredibly important in the field of astronomy. They give us a window into the universe, revealing the secrets of stars and their life cycles. And the best part, you don't really need a PhD to start appreciating these fascinating facts. With the right tools and a bit of curiosity, anyone can start to explore the wonders of the cosmos. What did you find most interesting about stellar spectra? Do drop a comment below and let's chat about it. And if you are eager to learn more about the universe, make sure to check out other videos on this channel for more insights. Don't forget to like, subscribe, and share this video. I'll see you next week. Until then, take care.